All right, we'll start doing some things with triangles and things in two different directions. This video is with our slides that go along with determining vector components, and we're going to talk about a resultant. So the idea here is predicting, well, not necessarily predicting, but explaining motion when it's actually going in two dimensions, kind of an X and a Y component. Up until this point, most of our directions and our movement has been linear, just on one line, like just on an X line, just moving back and forth. What you see in this picture is would be a boat going across the river. And so we see that the boat is trying to go across, but the river is flowing, and the motion of the boat ends up going in this kind of a northwest direction that we have here. And so what we want to be able to do is to kind of piece together all of this. And so this arrow is the actual motion, but you can see that it's composed of a combination of the boat's velocity and the river's velocity to get this total velocity, and it's making the angle right here. So largely that's what we're doing today. That's going to be called resolving a vector. We're going to try to break it into its X and Y parts on a grid. And then you can also think of the X and Y as being parts of the compass. So the X direction would be east and west, and the Y direction could also be thought of as north and south. So we're going to do this by turning things into a triangle, and we're going to use some mathematics to be able to measure things and get numbers for stuff. So first thing we want to make sure we do is remember parts of our triangle. We're going to be using right triangles today. So again, the little square in the corner tells us where the 90-degree angle is, and across from the 90-degree angle is going to be our hypotenuse. The other two sides are going to be our opposite and adjacent side. There's also this circle with a line through it. This is the Greek letter theta. We use it to stand for and represent an angle that we have in a triangle. Remember that the hypotenuse is always going to be the longest side because it's across from the biggest angle. You can't have an angle bigger than 90 degrees in a right triangle. Which one's the opposite and the adjacent can depend. So the adjacent's not always on the bottom, the opposite's not always on the side. These can be flip-flopped around. It depends on the angle that we tend to be using. So the way that this triangle is drawn right now, there's an angle down here at the bottom, and because we're looking at this angle, the side next to it is the adjacent side, because literally adjacent means next to and opposite means across from. If we're talking about this angle, then the bottom is the adjacent and the side is the opposite, just as it's labeled. However, if we went to the other side and we're talking about this top angle, then this is no longer the opposite side and this is no longer the adjacent side, because by definition, adjacent is next to the angle that we're referring to. So if this is our angle that we're referring to, then the side next to it now becomes side A, and this would be the adjacent side, and the side across from it would now be this bottom one, which that would be the opposite. So again, naming the opposite and adjacent, we have to define which angle we're referring to in order to be able to properly label those. If we know two of our three sides, and we want to find the third side, we can simply use our Pythagorean theorem. A squared plus b squared equals c squared. Remember, c is always the hypotenuse. A and b are the other two sides, and it doesn't really matter which one is a or which one is b, because in the formula, they're going to be added together. If we had an example where side C was 10 and side B was 4, just going through the math of us doing this, we'd start with our formula, plug our numbers in. So if C was 10 and B was 4, we would square each of those. 4 squared becomes 16, 10 squared becomes 100. Subtract 16 off of each side. That would give us a squared equals 84. And we want a, not a squared, so we need to take the square root of a squared to get a. So they would have to take the square root of 84 to get our answer. And ultimately, that would give us a side that's 9.2 meters per second. And notice these are not just meters, but these are meters per second, because what we can do is we can, instead of using actual sides of a triangle, we can turn these into vectors, and that's kind of what we're going to be working on today. So when we're working with these triangles, this could be any kind of vector measurement. So it could be a displacement, it could be a velocity, it could also be an acceleration. We can use the triangles to answer any of those. Now, on side 2 of our reference sheet, we've got these trig functions. So these things that I'm about to go over, we don't need to memorize, but this is what we need to do when we need to know, when we're trying to find a side, and we know a side and an angle. So we're going to know, for example, like today, we're going to know the hypotenuse and we know our angle, and we're going to try to find the two other sides. So these are the formulas that we see on our reference sheet. We don't have to memorize them. Oftentimes we rearrange them. So we'll notice here, where the sine of theta is the opposite side divided by the hypotenuse. If we're trying to find the length of the opposite side and we know the hypotenuse, then we're going to multiply both sides by the hypotenuse. And the formula simply turns into what we see over here on the right-hand side, whereas the sine now has hypotenuse with it, and the opposite has kind of lost its hypotenuse. So effectively, hypotenuse goes from the bottom of the fraction and just goes over and multiplies itself times the sine. The cosine formula does the same thing. And as of right now, we're not really using the tangent formula, but that's when we wouldn't know the hypotenuse. We have an example and it says, let's resolve a vector. That simply, again, just means to break it down into its X and Y parts. And so if we have a boat moving 85 meters from one side of the river to the other, and it's going 25 degrees north of west, the question may say, or we may be asked to resolve the vector again. That simply means how far did it move in the X direction? How far did it move in the Y direction? First steps, we need to draw it. Again, 25 degrees north of west means that west is my reference direction, and 25 degrees north of that pushes us to the north. And so that's the angle we're looking at. So our boat is moving 85 meters. This arrow, again, is a vector, and it's going to represent the length that the boat is moving. It's representing also the direction that the boat is moving. All right, so we know that the 85 is the hypotenuse of our triangle because we can turn this into a triangle. And we know that our theta, the angle, is 25 degrees. So we're going to turn this into a triangle. And so now our vector has X and Y components. So now the X component is the west and the Y component is the north. So in addition to saying it actually went 85 meters, I want to know how many meters west did it go and how many meters north did it go. And we can do this by using our trig functions. So in order to find the west component, we know that theta is the angle right here. This is 25 degrees. And again, to properly use our trig formulas, I've got to identify which one is adjacent, which one is opposite. Which is the north adjacent, is the west adjacent. Remember, adjacent means that it is next to the angle. So if this 25-degree angle is my angle, this west one is the one that is next to it. The north one is the one that's across from it. So west is an adjacent side. And since we are going to be using the adjacent side, the adjacent side is in the cosine formula. The cosine formula, again, is written as adjacent over hypotenuse, but we can rearrange it. And once we rearrange it, we simply then plug in the numbers we know. Theta stands for the angle. So our angle was 25 degrees, plug that in. Our hypotenuse was 85. So we plug that in. And in our calculator, we simply put it in this way, cosine of 25. And then you would want to close the parentheses there and then multiply that times 85. Gives us a decimal number that if we rounded would be approximately 77 meters west. That again, what that means is this part of my triangle would be represented by 77 meters. And then to get the north side, we repeat everything, except since the north side is the opposite, we no longer use the cosine formula, we use the sine formula. When we use the sine formula and rearrange it, it's going to be exactly like it was on the previous slide. The only thing that's different is that we replace the cosine with the sine function. So on the calculator, we would do the sine of 25 degrees, close up the parentheses, multiply that times 85. We get a different number because we're using sine instead of cosine. Since we're using sine, this tells us the opposite side. And that's going to tell us that I've moved 36 meters north. And that tells me my two sides of the triangle by knowing this one angle and the hypotenuse there. So our boat would have moved 77 meters west, 36 meters north. And there we go. If we want to do one more example with that, if we wanted to find the west component, 45 meters, 19 degrees south of west, again, step one, let's draw it. All right, we know that we've got a 19-degree angle, and on this one, I actually don't have it drawn, but if I'm doing 19 degrees south of west, all right, again, west is my base direction. And then if I'm doing 19 degrees south of west, then this is my vector and this is the angle that I'm talking about. The hypotenuse is 45 meters because that's what this vector represents. So apologies for the mess there. So just like we did on the previous example, I'm going to turn, I've got this vector that's eventually going to become my hypotenuse of a right triangle. And then in order for me to get the south and west components, then largely I'm trying to get the x component and the y component. The x component is going to be the west, and the y component, because it's going down, is going to be getting the south that we have there. All right. So I'm going to clear that out. All right. So if we want to get the adjacent side, we're going to use the cosine function. All right. So I can draw it out one more time for you. So this is going to be our 45. I'm going to turn it into a right triangle. Because I know this angle, then the side next to that angle is the one I just labeled A. So this is my adjacent side. The one across from the angle is going to be my opposite side. So again, this adjacent was representing the western direction, and this opposite side was representing the south. So if I wanted to find the western component of this 45 degrees, I'm going to use the adjacent side. And if I use the adjacent side, then I have to use the cosine formula, just like we did previously. So I wrote this one a little bit differently so we can see it. This is the way the formula is written on your formula sheet. But we can plug in the 19 degrees for the theta. We can plug in the 45 for the hypotenuse. And then we need to rearrange the formula. So to get the 45 off the bottom of the fraction, I need to multiply both sides by 45. So to get our answer is 45 times the cosine of 19. Plug that in your calculator. 45 times cosine of 19, hit equal. And our adjacent side is 43 meters. Again, that's how far west we're going. And then to repeat the same thing for the south, we just use a different function. We still know that theta is 19. We still know the hypotenuse is 45. Since we're going south, that was opposite the angle, and that tells us that we're going to be using the sine function. So again, our math is exactly the same as it was before. The only difference is instead of using the cosine formula function, we're using the sine function. So it's 45 times the sine of 19 is going to give us our opposite side. So that length of the triangle would be 15 meters. Thus, the vector component that's going in that direction is 15 meters. All right. So the vector that we originally drew that was 45 meters long actually took us 43 meters to the west and took us 15 meters south. So again, in sum, if we know two of our three sides, we can use the Pythagorean theorem. If we know a side and an angle, we can use our trig functions to be able to get the answers for these.